Okay, so today we're going to move away from floodplains and take a look at terraces and see how they form, look a little bit about what they actually are, their major morphological characteristics and so forth. And then at the very end, we'll take a look at a conceptual model that was put together by Mark Taylor, who's a professor in Australia, on the controls on contamination of terraces in general. Okay, so and this is covered essentially in your textbook on pages 254 through 262 of chapter 7. All right, so a quick definition of a terrace: it is essentially an abandoned floodplain. It is created by incision of the channel, and it's created as a result of channel disequilibrium. So that channel has actually undergone a threshold crossing event, which has caused the stream system to downcut or to incise, and that incision then has produced this abandoned floodplain, or what we're going to call a terrace. The terrace is composed of two morphological parts. It has the terrace tread, which was the old surface of the floodplain, and it has this scarp, which was created during channel incision. What we're seeing here is that we've had incision, and then down within this trench, the channel is starting to migrate back and forth and creating essentially a new floodplain, which we would say is inset into these terraces, that it is contained within or inset in that terrace sequence. All right, now because a terrace is essentially an abandoned floodplain, it is going to contain or potentially contain all of the types of lithostratigraphic units or depositional deposits that we find in a floodplain. So all of those things we talked about, the lateral accretion deposits, vertical accretion deposits, potentially splay deposits, levees, all of those features could be present within a terrace as well. But we're going to describe a few other things about a terrace, which is somewhat unique to them and doesn't occur with floodplains. Now, the first thing I want to stress is that these are created by some kind of an adjustment in the stream system, and it has to include incision in this case. So we've seen this diagram before. This is elevation versus longitudinal distance downstream. Here is our longitudinal profile. A nice equilibrium profile is generally concaved up with very few irregularities within that. We could actually calculate the energy at any position along this profile. And essentially, the system is perfectly adjusted to transport the sediment that's available. But if for some reason the channel has too much energy for the amount of sediment coming into it, either because sediment loads have decreased or because the discharge and the hydrology of the system has increased, the energy has increased, we could potentially get incision or downcutting, which decreases the slope until it comes back into an equilibrium state. All right, so that's the general idea. It's been portrayed by this balancing type thing. This was a diagram that was initially used all the way back in the 1950s by Lane, and it's been modified in various ways since then. This is a recent modification by James Allen from South Carolina in 2013. And it's showing that when you have sediment delivery, so the amount of sediment, which should also include size, coming into the system is equal to its transporting capacity. So the ratio between sediment delivery to the channel versus its transport capacity, what it can actually transport is approximately one, then it's balanced. We're not going to have any net change in the overall methodological features. Now that channel may move around. It may migrate laterally, it may migrate downstream through sweep and swing. We might get scour and fill occurring during flood events. So it's not a static feature, it's a dynamic feature, but those changes occur around some kind of a mean condition. We're not getting a significant change in its overall form. Now, what this is saying is that sediment delivery here actually increases. We have more sediment coming in than the channel can handle, and that will cause aggradation. So when the sediment delivery is greater than the transport capacity, we have a ratio that's greater than 1, and we're going to get aggradation. So that channel is just essentially going to fill up. And it gives you some examples here of when that commonly occurs. And then we have just the opposite as well. When sediment delivery to the channel is low, it decreases and is below that of the transport capacity, so the stream can carry more sediment that is actually coming into it, then we're going to have degradation or incision. And this is the primary mode through which we're going to get those terraces formed. All right, now that particular diagram emphasizes the importance of slope on energy, and slope being one of the primary factors that's going to adjust in response to either a change in discharge or a change in sediment characteristics, load, size, and so forth. This diagram is put a slightly different way. It's from process geomorphology from Ritterdal. And what it's trying to show is that the sediment hydrology, that balance between discharge and sediment characteristics, is really controlled by the underlying geology, the vegetation within the basin, and the climatic conditions. We can also put structural conditions in there too, things like tectonic activity and so forth. If we get a change in anything up here, we're going to get a change here, and then these changes will allow that channel to adjust in various ways. One way that the last diagram showed was incision, but it could be a change in channel width depth ratio, its sinuosity, its channel pattern, whether it's braided or straight or meandering, and so forth. So there's a wide variety of actual changes that can take place. And if we get into the fluvial class, we actually spend quite a bit of time looking at these different types of responses that commonly occur. But for this class, I just want you to recognize that any change in geology, vegetation, climate, and so forth is going to likely have land use cover. It's going to likely have an impact on the sediment load and the nature or sediment delivery to the channel, which might create these adjustments, either aggradation or incision, and incision, the terrace formation. It's not only those upland things that can adjust, but there's a whole variety of other anthropogenic impacts that could occur on these basins. This is just kind of a diagram. It's in your book, in your textbook. Gives you an idea of some of the things that we do as humans that might affect discharge, sediment loads, channel configuration. If we change channel configuration, say it's sinuosity, we straighten it, we're actually taking it out of equilibrium and it has to come back into equilibrium that way because we're changing the form rather than the discharge or sediment load. So those that sediment delivery, discharge, form all have to be balanced. It changes its form to come back into the equilibrium state. Okay. Now, Shum, back in '73, argued that anytime we go from a state of equilibrium to disequilibrium, we cross a threshold. So thresholds are essentially the limits to equilibrium. It is that state when we've changed the discharge of the sediment load enough that we've kind of impacted that balanced condition, gotten rid of it. And he said that these thresholds could be caused by three different things. So it could be classified as three different types of thresholds. Extrinsic threshold, the disruption was caused by something external to the system, like a change in climate, or change in tectonics, or change in land use cover. Those would all be extrinsic. Intrinsic is something internal to the system. Maybe it was change in weathering characteristics. Maybe it was a landslide that came down, brought lots of sediment into the channel, temporarily disrupted that system, something to that effect. And geomorphic threshold is a type of intrinsic threshold. It's really caused by a change in the morphology of the system. So maybe the kind of the classic argument is that you might have deposition on a valley floor, which increases the slope. And as that deposition and slope continue to change, it changes so much that we actually get a response. Takes that equilibrium. So external system, internal system, geomorphic threshold is a type of intrinsic that's related to a change in the morphology of the overall system. So we have these different types of disturbances that could lead to these channel changing events. The other thing, just really quickly to recognize, this is our response variable. We can say it's channel width, we can say it's channel depth, whatever. This is an equilibrium state, those things changing around some kind of a mean condition. Then we get, say, a big event comes through, it's going to make that channel extremely wide. That will come up, and initially the response is a bit of a lagging time between the event and the actual response, but once it responds, it occurs very quickly, and then slowly comes to a completely new equilibrium state, as long as those floods that did damage are kind of more frequent than the time it takes it for it to recover. Now, one of the important parts of a true threshold crossing event, I don't know why it didn't come up all the way up to where it's supposed to be up here, but anyways, is that it's a permanent condition. If it goes up, say the channel widens during a flood and then comes back to its pre-flood condition, the pre-event condition, threshold hasn't been crossed. So threshold crossing event is we've changed the system permanently. It doesn't go back to what it was morphologically before the event took place. All right, so let's get into the nuts and bolts here of our terraces. We don't want to spend a lot of time on this. We're going to have two types of terraces we're going to talk about. Erosional terraces, also called the strath terrace. So erosional or strath terrace. This is created by lateral planation. So the channel is in equilibrium state. It's moving back and forth across the valley floor. As it's doing that, it's eroding the outside in a meandering channel case. It's eroding the outside of the bank, putting down these lateral planation or lateral accretion deposits. This is supposed to be our point bar here. And as it migrates, it cuts a planar surface on here. So if we look at this terrace, what we see here is bedrock, and it's inclined at an angle. That bedrock surface has been planed off by this lateral planation, this movement of the channel back and forth across the valley floor, and then it's created these deposits on top of it. These deposits are of uniform thickness. So what we get then during this whole process, this may be composed of a whole variety of different kinds of deposits, but what we get is a suite of deposits that are of uniform thickness, and on the surface, it's planed off all of the rock units. Doesn't matter if they're inclined or whatever, it's just chopped them off, creating this nice parallel surface with very little, relief across it. So that is an erosional surface here. It's created by equilibrium conditions, migration or surfaces created at that level, and then at some point, we had a threshold crossing event, which then incised through that package of stuff, and the channel's now lower than what it was when this was the actual floodplain surface. So we've had a period of stability, equilibrium, and then channel incision, one threshold crossing event. Another picture here coming out of this canyon, you can see the bedrock. It's planed it off, nice uniform thickness here. Nice planar surface. Another one here, bedrock, planed off, and then we have this nice uniform package of stuff. Now, this doesn't necessarily have to be bedrock. It could be just older, unconsolidated sediments that are there that get planed off as well. But I just put these up because it's really easy to see this boundary between the bedrock and this nice upper floodplain materials. So that's an erosional terrace. Now, we can also have the case in which too much sediment's coming in, giving its transport capacity, and the whole thing just fills up. So the channel may fill up, may spill onto the valley floor, and it may grade the whole floodplain. Everything goes upward as we deposit sediment within that valley reach. And that's aggradation. aggradation will occur until it increases slope to the point where we can now transport the sediment downstream. So we've had one threshold crossing event to get the materials up there. And then we have a second threshold crossing event, which causes channel incision. So this is what it's kind of block diagram showing. We've had to have a threshold crossing event where sediment delivery exceeds transport capacity. We get aggregation to this point, and then a second disequilibrium event actually causes incision. So we have aggregation, there may be a period of time there that would stay stable, and then degradation. It might be that it degrades and then cuts back down, as we'll see in a minute, or in the next presentation or the next lecture, in something called complex response. Here's a diagram of it. You can see that it does not produce deposits of uniform thickness. These may vary. The surface at the bottom here does not necessarily need to be planar or smooth. It can have a lot of irregularities in it. And you can see one here for this arroyo, kind of what it looks like. This kind of looks, in this case, that this is kind of uniform thickness. You can tell it gets a lot fatter here. And then if we could actually look at this along the channel even further, we could see that it's really irregular in shape. All right, so in terms of contaminant histories, what we can see here from these two is that if we have an influx of contaminants, in this case where the channel's stable, it's going to be incorporated just in that uniformly thick material at the very top of the deposit. And these deposits here tend to be about maximum thickness of about 1.7 times the channel, bankfold channel depth along meandering streams. It's going to be less than that on gravel bed, many gravel bed streams. That's in marked contrast to something like this, where we have an aggradational or depositional terrace where we've had filling, because all of this stuff, all of this terrace materials may actually be contaminated. Sediments are coming into it, contaminants coming into it during this filling. And that commonly occurs in areas of mining activity. And we're going to see an example of that from California in the next lecture. So in terms of the total volume of material that we may have to remediate and the material that's actually contaminated, it makes a big difference on whether that terrace is an erosional terrace, characterized like this, kind of a thick uniform package near the surface of the terrace tread, or a big package of material where we had contamination occurring during filling, and then we had a renewed period of incision. In addition, if we have this case, there's going to be a lot more material in the valley that can be subsequently eroded and reintroduced to the modern channel system, where up here, the amount of material which may be eroded, contaminated material which may be eroded and reintroduced to that channel, that is going to be much, much less. All right. Now, one thing to recognize is that along any given river system, we may find both reaches where we have true terraces in one section of the stream, generally upstream, and then those surfaces, those paleo surfaces, may be actually buried downstream. So here we have a period of incision. This was the original channel gradient. In this case, it was pretty high gradient because it was associated with the last glacial episode. It was carrying lots of debris, very large debris associated with glaciation. But then when glaciation stopped, we had a climate change. Probably had lower flows, but finer grained materials didn't need those high slopes. And so it incised in these upper part and created these two terraces. So that incision was kind of episodic, occurred once and forget. But look what happens here. All this material in this upstream area that was incised and cut out, it was redeposited downstream on the valley floor. So if we look at the landforms and the distribution of the terraces along the river, we're going to get different things in different parts of that drainage basin. So in the upstream part, in this case, this is along Rio Topa Mile, what we have is these terraces, which have now been farmed, agriculture, floodplain, channel, terrace, and all of these terrace treads up in here. It was a type of fill terrace that filled up during mining activities, and we got incorporation of mercury as well as other trace metals through the entire terrace tread. And then sediment load's kind of decreased, and we've got incision in this area down to this level. If we go downstream, however, what we get is that the whole floodplain is just continuing to fill. And you can see that these dark layers in this sequence are actually buried soils or paleosols. And what it's showing is that we had terrace formation upstream. It buried that soil, created all this stuff. Then we had another period of stability, and then we got another renewed period and buried that. So we can have these different things along the stream. Now this is, in true honesty, this picture here actually came from Nevada, but it's giving us the same thing. I just simply didn't have a really good picture of the sequence that occurred along the Rio Pilcomayo, but this was happening along the Rio Pilcomayo. So we can have these kind of buried surfaces, paleo surfaces, often characterized by a soil in its surface that gets buried from the excavation of terrace materials upstream. So hopefully that's clear. We're essentially cutting down here, taking that material, and then burying the old surface, the old paleo surface, in the downstream area here. So there's no terrace treads or scarps down here. It's all subsurface, all buried. Up here we do have those. Okay, so then the last thing we're going to leave you with here is a model that was put together by Mark Taylor and his colleagues. He looked at a whole series of different terraces and some rivers in the UK, and he mapped out kind of the age of the terraces, where they were at, and particularly the age of the terrace relative to mining operations. So there was pre-mining terraces, there was terraces and deposits created during mining operations, and then there was sediments that were deposited after mining had taken place. And in these deposits, he looked at the different concentrations that existed. And from this, he was looking primarily at lead. Barium is one of those things that's often associated with lead zinc ores and then zinc concentration. So you can see in this case, this terrace right here had the highest concentrations, 155 ppm of lead, 344 barium, 222 ppm of zinc. So the point is that he went through and he looked at the stratigraphy, he looked at the morphology, he created a geomorphic history of this thing, characterized what those terraces actually looked like, the deposits within them, and then looked at the geochemistry. And from that, he created a model, a conceptual model. And this model is still pretty frequently used. And what it's saying is that in addition to the variations that you might get in a typical floodplain that would be, say, contaminated during mining operations, we have some other controls on these terraces, kind of that are going to control the concentrations of the contaminants within the terraces. So what are we looking at here? We're looking at, in this case, the influence of flood frequency, and one could say magnitude as well, when the channel is essentially in equilibrium. So we're not having incision or aggradation occur. And in pre-mining conditions here, we're depositing stuff, but it's all clean. Then we have mining era, we have really high concentrations, and the distribution, the volume of that material is going to depend on how frequently those terrace treads are actually inundated. So these two are inundated pretty frequently, this surface not at all. And then over here, what happens is post-mining, we're no longer bringing as much material and contaminants in. And so then we lay some clean stuff on top of these terrace treads. So we have really contaminated stuff, and then we bury it with cleaner materials. And the amount of stuff that's on top of those is going to vary depending on how frequently those terrace treads are actually inundated. More frequently inundated, clearly it's going to have more thicker contaminated materials on top. In this case, we're looking at incision. So a channel is undergoing incision. Pre-mining, it's fairly stable that it incises. And because it incises in here during mining period, and this has essentially closer to the stream, more frequent flows, we get thicker deposits, fewer deposits here. And then same thing after the event, thicker deposits on the lower one, and then clean materials on the surface that bury those things. So kind of gives us a sequence. In this case, we're having only lateral reworking. Those deposits are inset kind of down here in the valley floor as kind of this laterally planated package of debris. And then over here, the channel's incised slightly. It's kind of migrated back and forth more. And we have this stuff stuck within this terrace tread. And then this thing over here is kind of the clean materials, which occur a lot right along the river system. So it just kind of gives us an idea of where we would expect to find the thickest and probably most contaminated materials along the terraces, depending on the frequency of inundation and whether we get incision or lateral migration. And then also where we would expect them to be buried with clean materials after mining versus where we don't. So where are we going to get those clean deposits? So in this case, we don't have much clean deposits on top. That again is in the textbook. This whole discussion here, probably more detailed than what I've presented here, is in the text. So if you're interested in that, you can go back and you can actually read that and get a handle on it. Okay, so we're going to stop there. We're not going to say any more about these types of terraces. The next lecture, we're actually going to look at the impacts of hydraulic mining operations on rivers and terrace formation during something we call an aggradational degradation event, which is very common along mining impacted rivers and can really affect the distribution of contaminants along River Valley where they exist. Okay, we'll stop there.